Hello and welcome back to Let's Code Physics. As you can see from our animation here, we are getting back into our Drude circuit today. It's been a few weeks since we were in this. I wanted to take some time away from it to let my brain reset. That's usually a good thing to do with a physics problem. And we're going back to our parallel wires scenario here because I realized as I was getting ready for the next part of this series that I never actually calculated the current in these wires. I calculated the average velocity in each wire, but I never actually turned that into a current calculation. I realized this when I was trying to test a relationship about the current in the wire and the size of the wires. So you can see here I've got these wires as the same length, that's the direction of the electric field going that way, but I've got one of them having a larger cross-section than the other. The wire with a larger cross-section is supposed to allow more current through. You can see I'll show you how I got this, but I do have the actual current calculation here, so it's no longer just the electron velocity subbing in for the current. This is an actual calculation of the current. And the red graph on the top is the current for the larger wire here on the bottom, and the green graph is the current for the narrower wire, the one on the top. And you can see that they've got a pretty significant difference there. There's some oscillation going on, as we've seen before. It tends to level out. That's why I don't bother graphing it till after 20 seconds. But what you can see, we've got an average for the green of about a quarter. We've got an average for the red of about 1-ish. And so the red current is about 4 times as large as the green current, which is what you would expect because the area of this one is 4 times the size of the area for the top one. So now that I've shown you the ending, let me show you how I got there. So what we're trying to test here is not just how Ohm's law works. So we've seen that Ohm's law is pretty well verified, this V equals IR business, where you've got the voltage here that is the potential difference that you set across here that is creating an electric field. The electric field works to accelerate the electrons, but the electrons have these random scattering events, and so their velocity is mostly in the direction of the electric field, although actually electrons go opposite of the electric field. But just let's just pretend that we defined our charges the right way for a minute. I'm sure I'll hear about that on Reddit after this goes live. So as this, because of the resistance in this thing, you end up with a relatively constant current going through the wire because of the scattering. So the electrons will accelerate, and then they get scattered, and they accelerate, and they scatter, etc., etc. What we want to combine that with today is the standard calculation for resistance. So the way we get this resistance, if I can get my cursor back, there we go. The way we get this resistance, so this resistance is an extrinsic property, meaning it is a property of the wire itself. It depends on the wire's shape and size and dimensions and everything. And so what we have is an intrinsic property called the resistivity rho. What this means is this is a property of the material itself. So this depends on whether the thing is made of copper or iron or whatever kind of conductor you are working with has a different resistivity. So this is a function of the material alone. Then we've got the length of the wire. So that's the length going in the direction of the electric field. There we go. So we've got length there, and then we divide by the cross-sectional area. So that's the area of whatever shape it makes when you slice it like this. So in this case, that would be a circle. At least I try to draw a circle. For our simulation, we're dealing with a square. So you just use whatever formula for the area you have there. You know, from 5th grade or whenever it was, we started calculating areas. So you know, your good old pi r squared, length times width, etc. Or not length, I should say, width times height, etc., width times depth, whatever nouns you'd like to assign to the 3 dimensions. And so what that means is if I plug this in to the Ohm's law equation, so the voltage across is equal to I rho L over A, that means I can determine the current from all this other stuff, right? Because this is stuff I can set up in the in the code. So if I take this and solve for the current, sidebar, I have never really been comfortable with this formulation of Ohm's law. I really prefer I equals V over R, or even better, I equals V times the conductance, because you don't create a current and get a voltage, you create a voltage and get a current. We just write it like this because there's no division involved. But anyway, soapbox done with. So this means that I is going to equal your voltage times the area, because we're multiplied by the area, and then divided by the other two things. So divided by the resistivity and the length. And basically what that means is that the longer you make this wire, the harder it's going to be to get current through, because it's got more collisions. Each electron has more collisions to encounter before it reaches the end. The wider you make it, the better you're going to get, because then you're not just changing when the collisions happen, but you're also increasing the number of electrons that you get per unit length. And of course, the more you ramp up the voltage, the greater your current's going to be. So this is the thing that we're going to be testing today to see if our code successfully produces that. So the first thing I need to be able to do is I need to be able to actually calculate the current and not just do a hand-wavy argument about the velocity being equivalent to the current. So what I've done is I've set up a new variable here, this AVGC for average current. I suppose I can put a comment here. It's actually technically not the average current. It's going to record the total number of electrons, but we'll just call it AVGC for right now. The way I'm calculating that is I'm returning to this piece of the code where the wire wraps back around on itself. So if an electron ends up at the right edge with a positive velocity, meaning the electron ends up over here, and let's even draw an electron, meaning the electron ends up right here and is about to zip out of the right edge. What it's going to do is it's going to be transported back over here to the left and re-enter with the same velocity. So if you like, I've put one portal over here, I've put another portal over here. In more physical terms, what it's doing is, say this is where the battery is located. Imagine we've got the wire wrapped back around on itself with a battery in the middle. And this would be where the two ends connected. And so what we're doing there is we're saying, okay, that's the point at which I'm going to count electrons passing through, because current is basically the number of electrons passing through. Current is the amount of charge per time. So you can make that equivalent to the number of electrons per unit time if you just factor out the... So if that happens, then our current is going to increase by 1. So this is keeping track of the number of electrons that have passed. So we're going to increase number of electrons that have passed by 1. And that's all well and good, except that I also need to consider the opposite case, right? Even though I have an electric field pointing, say, to the right in this case, there is a probability that an electron will be at the left edge with a leftward velocity. And that means it needs to appear back at the right edge with a rightward velocity. So these two electrons passing right and left, those need to cancel each other out, because that's a net gain of nothing, a net passage of nothing, if you will. So that's where we have this part, where we have if the electron is going opposite the direction of the electric field, then we're going to decrease the number of electrons that have passed by 1. Copy and paste. And I've got this set up in terms of the electric field because I want to be able to turn the electric field from right pointing to left pointing, and have the calculation still work. So then I have the same things down here. I'll paste that in here. Spacebar, paste. And so these 4 possibilities just keep track of how many electrons have passed in the direction of the current and how many have passed opposite the direction of the current. In terms of an experiment, this is equivalent to placing an ammeter here, a current detector here. So if you like, for your circuit diagram, you can put an ammeter here. And so basically we're calculating the current through that ammeter, which is pretty cool. Let's see, the next thing that I had to add in getting ready to set up more complicated circuits, I need to start thinking in terms of voltage and not just the electric field. And so the electric field is determined by the voltage per unit length. I made a mistake in my first video in this series. which ironically I did not get slammed for on Reddit. For all the discussion that generated, nobody pointed out that I made a mistake with that. Maybe it's because I admitted to it in the first comment on the video. Who knows? So what we're doing here is we're setting up the electric field in the wire as the voltage across the wire divided by its length. And then we're setting up the length and the width of the wire. As you can see, we've got the length set up the same, but the width is going to be 2 times the width of the second one is going to be 2 times the width of the other one. So I commented that the area was 4 times as big, because when we go to calculate the volume, so down here I've also added in a volume calculation. Let me go up for that one. When we calculate the volume, where are you, volume? There we go. We're taking the length times the width squared, right? So this is a rectangular prism with a square cross section. So we've got width times the same width times the length along the electric field. So we've got that volume. The reason I wanted to calculate the volume is because in order for this Ohm's law and resistance definition business to work, we've got to have a consistent electron density between the wires. I'm eventually going to move that definition into the wire itself, and we'll probably just have the electrons created inside the wire, so we don't have to set up the electrons separately, because basically once you have this and this density and the dimensions, you can spawn in the electrons inside the wire. So I think I'll move that up to the wire instantiation off camera. So what we're doing here is we're just saying to create a number of electrons in the wire that's equal to the electron density times the volume of the wire. So electron density is number of electrons per unit volume, a very important thing to calculate in condensed matter physics. So it's like mass density. If you're more familiar with mass per volume from chemistry, it's just number of electrons per volume. It's a different type of density. We multiply that by volume, we get the total number of electrons. Let's see, this thing, the second one has 4 times the volume of the first one, so I should be getting 4 times the number of electrons. So I'm printing the number of electrons there. Let me just double check, make sure that is working out appropriately. All right, so we're going from 61 to 241. So apart from a counting issue of me still not knowing how to set up loops, 60 times 4 is 240. They each get an extra 1. 1 out of 60 and 1 out of 240 is not going to make that big of a difference, which is cool. Let's see. So we've the other thing I'm doing now, I was previously having all these start in the center, and that was that was throwing things off because the electrons had to spread out. So now we're just randomly distributing the electron positions within the wire. And then down here we are graphing the current. So the way we're doing that is we're taking the number of electrons. Remember, ABGC counts the total number of electrons. The more and more I think about it, I should probably change that variable name so that it's clearer. And then we're dividing by the total time that has passed. So this is the number of electrons that have passed through that particular plane of the wire per unit time. So it's doing the work of an ammeter for us. So let's see, we've already seen this scenario that it works, that the width is 2 times, so the area is 4 times, and so we've gotten 4 times the current. So we multiplied this area by 4, we got 4 times the current. So that part of this equation is working. Let's check on our voltage. Let's see what happens if we make the areas the same. So we're going to make identical dimensions of the wires. Let's double the voltage of the one on the bottom. Actually, let's double the voltage of the one on the top, so that way our graphs will visually line up with our wires. So now I've got 2 identical wires, and what I've done is I've set the top one up with a battery that has twice the voltage of the battery that's set up on the second one. I need to actually create a visual for the batteries for when we get into actual circuits. And lo and behold, this thing is, so we have to wait for them to level out. So I started at 20 because I was getting these huge peaks at the beginning, because basically, you get 1 electron to go through in the first second, there's a huge peak, and there's a non-electron second section, and so there's a huge dip. And so I did this to give them some time to level out. Apparently I did not give them enough time to level out. You can see the data is kind of noisy here at the beginning, but then they are starting to level out. Part of the reason for that is we're taking the total number of electrons divided by time. So if this remains consistent for a little while, then this is going to decay like 1 over time. So that's why you see this kind of 1 over time structure here. But it is gonna level out. Looks like after 100 seconds. Let's see what we get here. Here I've got a current of about 0.2. So let's call that 0.28. Here I've got one of 0.48. So that's not quite doubled. So I suspect what do I probably need to do to fix that? I mean, it's on the order of doubling, right? Or here we've got a 0.29. I mean, it's climbing up here now. I'm wondering if I increase the electron density, if that would help matters. Let's up that to say 15. I mean, it's an arbitrary number anyway, but with a greater density, it's more fluid. Basically, you're making better fluid approximation, so you're getting more electrons passing through per unit time. So hopefully that'll level these things out a little bit better. And of course, now that I have more electrons, my code is running slower, so it's going to take longer for it to reach that 20 seconds. So I might cut here and wait for the... Oh, here they come. Actually, yeah, let me cut here and let these graphs level out for just a minute. I've gotten a second monitor hooked up, so I can now have my notes on a separate screen so that I don't have to be alt-tabbing back and forth between them. But the other thing I've discovered I can do is I can record when my cuts are as I'm recording, as opposed to having to go back and finding those. So I'm hoping that will lead to fewer instances of me coughing and blowing my nose on the episodes. So that's a handy tool. So what we've got here is these have leveled out a little bit. We've got about a 0.6 here. And around a 1.2 here. It's a little high, 1.4, but the last one was a little low. So in terms of order of and as Griffiths comments in his E&M textbook, it's a miracle Ohm's law ever works out at all, because it's this average of all these things flying around in a metal. So let's call that one pretty much verified. Up to issues with the number of electrons. Let's put this density back down to 6. That was running a bit smoother then. Finally, I think we're pretty confident about that the resistivity will work out. We've seen that hinder the... Let's last try the length. This is the one that I think is probably the most counterintuitive for students, because you're working with this thing and you think, well, if I make it... Well, one of the two needs to be counterintuitive, it seems to me, because they're both making the thing bigger, but they don't do it in the same way, right? So we're used to thinking in terms of density, where you make any dimension bigger and you make the mass bigger. But resistivity is more nuanced than density is, because resistance is more nuanced than mass is, because the length increases the resistance. The area decreases the resistance. So we just saw that a change in the area... an increase in the area increases the current. Now let's see if an increase in the length decreases the current. So let's make one of these wires longer than the other one. So let's see. Let's put our voltages back to the same. And this time, let's make the lower one have 2 times the length of the upper one. And again, the goal is to see the change in the current. Now, what's changed also since then is the number of electrons, right? So now that this bottom one is twice as long as this one, it's going to have twice the number of electrons. But it's still got the same number of electrons per cross-sectional area, if you will. And so the question is whether that's going to... the question is how that's going to impact the current, whether it's going to impact it like we expected. So we're expecting the one on the bottom to have a lower current. In fact, we're expecting it to have about half the current of the top one. And of course, these things are still leveling out, so I'll take another cut here to let my data settle down. I forgot to mention the other factor that changes when you increase the length. So you are doubling the number of electrons, and we see that over here on our printout screen, we go from 60 to 120. You're also changing the electric field, right? Because when you double the length, you're decreasing the strength of the electric field. So that's the factor that's really important with changing the length. So the area is important. So I guess I got myself a little confused earlier. Changing the area is important because you're changing the number of electrons that can be contained in the wire. Here you're changing the number of electrons, but more importantly, you're changing the electric field. So the electric field is being cut in half. And let's see if my data is agreeing with me now. Okay, so they've settled down a bit. So let's see, here we've got about well, now it's decreasing. So if I take the average of this valley and this peak, that'll be about here-ish. So we've got about 0.18, so I'm expecting this one to be 0.15. You get, see, if you double 15, you get 3. If you double 16, excuse me, if you double 18, you get 36. So I'm expecting this one. So this one's a little low. This one's giving me just under 0.3. So this is not quite the cutting in half that we expected. Again, that might improve if we increase the number of electrons. So let's do this. Let's make this super duper dense. It'll make the code run slower, but here's what I'm going to do for you, the viewer. I am going to put this next part in fast motion so you can see it unfold. So what we've got here is is about an average of a half. I'm going to call it a half because, dang it, it's pretty close to a half. And also, this one's pretty close to 1. Actually, it's dipping down now. But we're getting a little bit better result here now that we've added more electrons. So there's sort of this stabilization time, as it were. That's, you know, when you do a real circuit lab with real circuits and real ammeters, you're getting a nice steady reading, hopefully, with a DC circuit anyway. And so that just shows you, I think that, you know, there's a whole lot more electrons at work, right? So I've got, you know, hundreds of electrons as opposed to, you know, Avogadro's number of electrons, you know, at work in a real circuit wire. I think I've decided the title for this episode will be "We Need More Electrons," because that seemed to be what I kept having to do. So anyway, now that we've got this set up, we've confirmed that all the aspects of this lovely equation are working for us. We've got the voltage working, we've got the area working, we've got the length working. I suppose we didn't test the resistivity, but I think we tested that plenty in a previous video. So what we get to do next is we get to start actually building circuits out of these things with parallel branches and things like that, and that's where we'll need all this voltage business to work for us. So we will start that next time. I look forward to seeing you then. Have a great day. Bye-bye.